Now, these crazy little things do very, very um, kind of interesting, to say the least, sort of functions depending on their arrangement in space. So, um, for example, if you have a proton, and you bring them, I mean, any distance apart, there is actually going to be a force associated with this arrangement. Um, and the reason why this happens is beyond the scope of this video, but basically this force that happens here is going to be proportional, inversely proportional to the distance between the protons. So the higher the distance, or the greater the distance, the less the force. That is to say, as you bring these two protons closer together, there's going to be a greater force, uh, a greater repulsion force. Um, Same with putting two electrons together. They just don't want to be anywhere next to each other, and the same exact rule applies. And then there's there's an equation associated with this arrangement, which tells you exactly how many newtons, which is the standard unit of force. How many newtons exactly will be present here at this distance, but you don't have to worry so much about it. That's too much detail. The interesting thing is, though, that neutrons don't interact at all. There's no anything. There's no force between them. Nothing, nothing, nothing. There's also no force between them and a proton, or a neutron and an electron. There is no force whatsoever. However, the interesting and key point is, if you bring a proton and an electron, there's going to be a force associated with this in the inverse direction. That is to say, if I have a proton here and an electron here, the proton is going to try to pull the electron towards it, and the electron will try to pull the proton towards it as well. So, and again, this is associated with D. F is inversely proportional to 1 over D. So because of that, we can actually get some pretty interesting things happening because of those properties. Let's say copper, for example. So in a solid, as you hopefully already know, you have, actually let me do something else. What you have is very tightly bound atoms, or nuclei, I should say. They're in a solid. All the nuclei are relatively close together, right? And okay, I'm just going to denote my copper nuclei with X's like this. So you have a bunch of nuclei here and there inside of this material, this copper material. And also you have electrons, which I'm just going to denote with circles. I should make little circles everywhere inside of the copper material. Now, as you have learned in chemistry, you should know that every nucleus wants to have a certain number of electrons flowing around it. It has to do with, subshells and energy levels and whatnot. But the main important thing to understand is that for the most part, any point in time, every nucleus has a certain number of electrons around it. But here's the key point. Why did I even talk about copper, which is Cu, in the first place? So Cu has 29 protons, and I don't remember the notation, so I'm not going to try to do it, but it's 29 protons, and it actually has 34 neutrons. So if we're talking about neutral copper, if you have 29 protons, then you also have 29 electrons around each nucleus here. So you have a lot of electrons, and as you may already know or realize, the further away, I mean, actually, as we've talked about already, um, the further away the electrons are from the nucleus, the weaker they are bound to that nucleus, right? Because the distance is greater, and so the force between the nucleus, which we can just technically say it's positive because there's there's just a bunch of protons and neutrons in there. So as that distance gets greater, like we said before, the force of attraction between the electrons and the protons or the nucleus um, decreases. So the electrons way out here that are kind of far away from either of the nuclei, they're sort of weakly bound and get lost. And so they're going around their host nucleus, but then every so often they'll just switch, and then oh wait, this one's maybe better, and then I don't know, maybe this one, and then this. So they keep doing this, and not just one electron. I mean, all of them are doing this at the same time. And the key point is though that over a long enough period of time, that is, I don't know, after a fraction of a second, um, that even though this electron will go this way at one point, over the entire course of its path traversal, it'll not go anywhere. Um, I mean, it'll do crazy things, but eventually, or overall, I should say, it stays in kind of the same area. Um, and that's kind of really important because if it didn't do that, then the next property would be pointless or much harder to control. Um, so now imagine that you still have all this happening here, but let's do something kind of, and I'm not going to explain how, because let's just say it's by magic, because I don't have a better way to say it. Let's just say we put a bunch of protons on one end. I mean, let's just say there are many more than I've drawn here, but anyways, so by some magic force, I don't know how, it doesn't really matter how, we've been able to get a lot of protons, so a lot of positive material in here. So overall, net positive charge. What is going to happen? So opposites attract, and so these electrons, I mean the ones that are close here, are going to be like, oh awesome, there's a lot of positive charge there, I want to go there. And then they're going to go this way. Now, technically, let's say this piece of copper is like really, really, really long. So let's just say that the ones out here, the electrons out here are so far away that they don't even feel this force. I mean, they do feel it. At any distance, they will feel the force. But let's just say, for our purposes, they don't even feel the force. It's so small that it's insignificant. So what you're going to have is these little electrons here are going to be like, oh, awesome, there's a bunch of protons here, let's go. So they all go this way. Now, what happens next is you're going to have, in the next instant of time, a gap, sort of. So all the electrons that were here, why is this pen doing that? All the electrons that were here are now here, right? I'm sorry for these lines, I don't know how they're happening, but so you understand, hopefully you understand that, so they were all attracted and they went in here. But you still have a bunch of, nuclei. So you still have a bunch of electrons out here, and now, like I said before, electrons, they repel each other, right, if they're too close together. So over a longer period of time, this guy over here is going to be like, oh, well, I'm doing crazy things, but there's a lot of, on this side, there's a lot of negative, and on this side, there's a lot of, well, here there's positive, but here, there's nothing. So would I rather be next to negatives or next to nothing, or even better, next to some protons here, or nuclei? Well, I'd rather be there. So over time, slowly, it gets here. But as soon as it gets here, then, oh, wait, there's a lot of positives here. Boom, it goes here. So technically, if this is a big enough source, all your electrons should eventually get here. Or not all, but a large majority of them. And if you've thought about this carefully enough, or if you've realized it by now, we've actually just defined current.